These notes are going to talk about the periodic table. On the periodic table, we're going to look at the mass number, the atomic number, and the atomic symbol. We'll also get into counting electrons and what the different areas of the periodic table mean. Let's talk about the atomic number. The atomic number is the whole number written in the box for the particular element. It tells us the number of protons that are there. If the atom is neutral, it's also going to tell us the number of electrons. So for example, here we have carbon. The atomic number is 6. That means it has 6 protons. And when it's neutral, it also has 6 electrons. Calcium, if you look on your periodic table, has an atomic number of 20. This means it has 20 protons. When it is neutral, it has 20 electrons. We also know that calcium, being in the second column, likes to give off 2 electrons. So when it's in its charged ion state, calcium has 18 electrons, but still has the 20 protons. Let's fill in this table. So for the element potassium, it has the atomic number of 19. This means it has 19 protons and 19 electrons. For the next row, it tells us that the electrons, there are 5 for a balanced neutral atom. If we look on our periodic table, the atomic number 5 goes with boron. This also means that there are 5 protons. If sulfur has an atomic number of 16, that means there are 16 protons and electrons. Vanadium has 23 protons, so it's going to have 23 electrons to balance that out. It will have an atomic number of 23. The mass number is the number of protons plus the neutrons in an atom. This number is not found on the periodic table. To get the number of neutrons from this number, you can subtract the mass number minus that atomic number, or the number of protons. Here are some examples of ways to write elements. If you see this first one here, we have the symbol carbon, we have its mass number of 12, and the atomic number of 6. If we want to look at carbon and see how many neutrons are there, we are going to take the mass number 12 and subtract out 6 to get 6 neutrons. Below you have it written in a slightly different way, where you have the element name and then the mass number. So silicon 28, silicon from our periodic table has an atomic number of 14, so we can write it in the symbol form. Or we know that if we take 28 and we subtract 14, we would get 14 neutrons in this case. For hydrogen 1, we have only 1 proton available there. There's also a hydrogen 2, and then if we wrote out hydrogen 2, we could see that we would have 2 over 1 H, or we would have 1 neutron here. Let's just practice with gold. So here we have gold 197. So AU is a symbol for gold. How many protons does this have? It has 79. We get that number from its atomic number. This isn't charged, so we know that it has 79 electrons. To figure out the neutrons, we're going to have to subtract the 197 from the 79. This gives us a neutron count of 118. Here are a few more practice problems. We have beryllium with the atomic number of 4 and the mass number of 9. So it has 4 protons, 4 electrons, and then 9 minus 4, so 5 neutrons. Neon would have 10 protons and 10 electrons from their atomic number, and then the mass number minus the atomic number would give us 10 neutrons. Sodium has an atomic number of 11, so it has 11 protons and 11 electrons. With a mass number of 23, we're going to subtract out the 11 and have a neutron count of 12. For oxygen, we have proton and electron count of 8 from the atomic number 8, and neutrons would be the mass number minus the atomic number, so 16 minus 8 is 8. Looking at bromine, we have 80 minus 35 to give us a neutron count of 45. We also have 35 protons, 35 electrons. For lead, we have 82 protons, 82 electrons. Then for the neutron count, we do 207 minus 82 to give 125. For sulfur, we have 16 protons, 16 electrons, and then 32 minus 16 to get 16 neutrons. Last one for silver, we have proton count of 47. We have 47 electrons, and then we have 108 minus 47 would give us 61 neutrons. So here's our periodic table, and it's set up in a very unique way so that we can describe how the atoms and elements give off or take electrons. So I'm sure that you remember back to the 8 is great rule, and that each atom would like 8 electrons in its outer shell. When I talk about shells, I'm talking about this picture up here. So you may remember drawing these where we had chlorine in the middle, and then you draw one row, one circle for 2 electrons. That kind of takes care of this top row here. And then you do another row that has 8, so that would be dealing with this row right here. Then you have this fourth row, or this third row on here, that fill up, and it only has 7 electrons on there. Well, these are the orbitals, and chlorine wants that last orbital filled. So it is wanting to add one more electron to give it 8. Now, if it adds this electron, it becomes negative. So that's what we say by the nonmetals. They hold their own electrons, and they can even grab other electrons to make this negative charge. So with this, that causes us to have very similar charges for columns on the periodic table. So the one involving chlorine, these guys tend to be a -1 because they only need that one more valence electron to get that 8 in their outer shell. The column starting with oxygen, they need 2, so they're going to take on 2 electrons, and the group with nitrogen, they need 3. And it's easier to take on these 3 than to get rid of 5 electrons, or it's easier to take on 2 and become negative than to give off their 6 to get to that 8. So we're really kind of looking at which one is easier to get that last outer row filled. So if we look at these orbital drawings of something like magnesium, we see that magnesium can fill out that inner 2, it can fill out the next row of 8, and then it has 2 additional ones left over hanging out here. Well, it has 2 options. It can either give these 2 electrons away, or it can add 6 on. It's easier for magnesium to give these 2 away. If it gives 2 negative charges away, it becomes a +2. So we see that this happens for this entire column on the periodic table. Similarly, the first column, they would only have one electron in the outermost shell, and it's definitely much easier for them to get rid of that one electron than to gain on 7. So we see that the first column has a +1 charge. Now, the portion in the middle, if we notice, these down here, all of this area through here, they don't really have that set number of orbitals because we start getting into some funky shapes that our electrons are going on. So it kind of depends on what the environment is to how many electrons these either give off in this case. So this is where we have to use those Roman numerals. And we'll talk more about those when we get into ionic compounds and really naming those. But we can have +2s, +3s, +1s, +4s, all in this area. The exception is this little block that's right in through here. And they have very specific, every single time that they react, they will react in silver giving off just one electron, so becoming plus. Zinc and cadmium will always give off 2 electrons, becoming 2+, and aluminum and gallium will always give off 3 electrons, becoming 3+. Now the rest of those all can vary in their parts, but silver, cadmium, zinc, gallium, and aluminum will only give those specific types of, or that specific number of electrons.